brings out a sexy three. If you want to talk to her, it don't matter. You'll be breathless when she calls.
So we're going to do some examples for tangent planes, linearization, and differentiability. So our first example gives us this function, f of xy equals x squared minus 3y squared. And at the point -1, 1, -2, we're asked to find the tangent plane at that point. So to do this, we need to find what the function is at this point. And I realize this example doesn't make any sense because... Okay, it does make sense. So this is the function value at that point. They give us f of -1, 1 equals -2, and we can just check that. We got -1 squared, which is 1, minus 3 times the 1 squared, which is -3, so it's just -2. So that checks out. So we got that. Another thing we need to find f or df dx of xy. So I'll just write that here. df xy dx, and that's just going to be 2x because this y term will go to 0, 3y squared, and derivative of x squared is 2x. df of xy dy would just be -6y because the x squared would go to 0. So now we're going to plug in our -1, 1, and since we just have x, or this should be f, we'll keep our notation consistent here. This is going to be 2 times -1, so we have another -2. df of -1, 1 dy is -6y times, with 1 as y, so -6. And now we just use our tangent plane equation, c minus z0 equals, or I'll put z minus f of -1, 1 equals df of -1, 1 dx times x minus, and here we're going to put the x value, so -1, plus df of -1, 1 dy times y minus, and here we're going to put our y value 1. So, you know, f of -1, 1 is -2, so minus -2 is plus 2. The x derivative is -2, and it's going to be times x plus 1, and plus the y derivative, which is a -6, so it's actually going to be minus 6 y minus 1. And that's our tangent plane. So our next example, we're given f of xy equals ln of x squared plus y squared, and we want the tangent plane at 1, 1 ln 2. So the function value at 1, 1 we already know is ln 2, and we can check that quick. 1 squared is 1, 1 squared is 1 again, 1 plus 1 is 2, so we have ln 2. Our x derivative, and I'll use this notation now, is 1 over x squared plus y squared times the x derivative of that, which is 2x, and likewise our y derivative is 1 over x squared plus y squared times the y derivative of that, which is 2y. So our fx of 1, 1 is 2 over 2. So 2 times 1 over 1 squared plus 1 squared, which is 2. 2 over 2 is just 1. And same thing happens for y derivative. It's going to be 2 over 2, so we're going to get 1 again. So our tangent plane, z minus z0, equals fx of 1, 1. And yeah, I should write this as f of 1, 1, x minus 1, plus fy of 1, 1, x minus 1. We know this is ln2. We know this is just 1, so we can drop the parentheses. And this is also 1, so we can drop the... This should be a y, my bad. Y minus 1. And we can combine the negative 1s to make a negative 2. And that's good enough for me. So, next example, we're asked to we're given f of xy equals x squared e to the y, and we're told to find the linear approximation at 1, 0. So this is the same thing we've been doing. The tangent plane equation is just the linear approximation. We've got to solve for z. So our f of 1, 0 is just 1 squared times e to the 0. These are both 1, so we can just rewrite this as 1. Our x derivative, partial derivative, is 2x times e to the y. E to the y is just a constant in terms of x. Our y derivative is x squared e to the y. X squared is just a constant, so our x derivative at 1, 0 would just be 2 times 1 times e to the 0, which is just 2. Our y derivative at 1, 0 would just be the same thing as our function value, because our y derivative and the function are equal, so 1 again. So tangent plane equation looks like this at the point 1, 0. And plug in the values. And if you solve for z, we get z equals 2x plus y minus 1. And this is our linear approximation. So now we're asked to, for this same question, they want us to approximate f of 1.1, 0.1. So you can see that plugging this into the original, trying to do 1.1 squared and e to the 0.1 would be pretty difficult. So what we do is we plug it into this linear approximation. So L of 1.1, 0.1 equals 2 times 1.1 plus 0.1 minus 1. This is just 2.2 plus 0.1 minus 1. You can just write this as 1.1 plus 0.1, or 1.2. The answer is 1.3. So f of 1.1, 0.1 is approximately equal to 1.3. So now we're asked to do another one of these.
These are the good times in your life, so put on a smile, it'll be alright. These are the good times in your life.
So number 4, and this time our f of xy is tangent x plus y, and we want to find L xy at 0, 0. And then use that to approximate f of negative 0.1 and negative 0.05. So again, we're going to plug in the f of 0, 0. That's just going to be tangent 0, which is 0. Our x derivative is secant squared of x plus y times the derivative of x plus y, which is just 1. And our f of y is going to be secant squared x plus y. Again, derivative of x plus y with respect to y is just 1. So our x derivative and y derivative are actually going to be the same. So we're trying to find secant squared of 0 plus 0, which is just 1 over cosine squared 0. Cosine 0 is just 1, and 1 over 1 squared is just 1. So tangent plane, so this is just 0, so where z equals x plus y. And this is our linear approximation. So now if we want to approximate f of negative 0.1 and negative 0.05, we just plug it into the linear approximation. So this will end up being negative 0.15, and that means f of negative 0.1, negative 0.05 is approximately equal to negative 0.15. So now we'll do a couple of differentiability problems. So this would be number 5. So we're going to do an example on differentiability, and we want to show that f of xy equals e to the x minus y at 0, 0 is, we're going to show this is differentiable. So we can find the partial derivatives, and that would be e to the x minus y times the derivative of x minus y with respect to x, which is just 1. And this is e to the x minus y, but we get a factor of negative 1 out here, because derivative of x minus y with respect to y is minus 1. So now we just need to check that these are continuous at 0, 0. So check continuity, we check does f of 0, 0 exist? That's just, or fx of 0, 0. So that's e to the 0 minus 0. Just e to the 0, which is 1. So it exists. Take the limit as xy approaches 0, 0 of e to the xy minus 1. We get the same thing, which is 1. So it exists at 0, 0. The limit exists at 0, 0. Those are equal to each other. And if you do f of y equal at 0, 0, we also get e to the 0 minus 0 with the minus sign out here, and that is negative 1. And if we take the limit as xy approaches 0, 0 of e to the, or negative e to the x minus y, we also get negative 1. So the partial derivative with respect to y is also continuous at 0, 0. So since these are both continuous, since they're both continuous at 0, 0, f is differentiable at 0, 0.
How do you think I can make you feel better? How do I know what you say is real? Writing an imaginary love letter, talking mostly about a sexy piece.